I know. But look at that.
Welcome, EECS16A. Woo!
Very good. Thank you. They are so polite, though. Okay. What were we talking about last class? Oh, it was such a long time ago. There was a weekend in between, homework in between. Yeah? We're talking about capacitors, remember? We brought capacitors to class. Some capacitors made it back to our offices, others didn't. We showed you in practice how charge sharing works, right? How you can take the charge from one capacitor, connect the other, and then share the charge. Exactly. Sparkles. Okay. We showed how to break the dielectric constant of air with incredible amounts of voltage. 1,000?
100,000.
100,000 volts. And now we have to formalize all of that. We started doing some formalization. We used our methodology of looking at, of solving the circuits for potentials and currents. We looked at the capacitor as a new element where we would still define a current and a capacitance and a voltage across the element. And then we saw that the IV characteristics now for the capacitor would be when we plot the current versus the gradient or the change of voltage with time. And we also said that here we are going to consider steady state, but in 16b you're going to see what's changing with the capacitor, how it gets charged, and so on. And then we said that the IV relationship for the capacitor, just like we have for the resistors, Ohm's law, for the capacitor, we would have this, where we would write I element as a function of C, which is capacitance, means how much charge you can store in your device, and capacitance dependent on what? On the permittivity of the material, the properties of the dielectric that you are using, if you're using a polymer versus silicon dioxide, etc. And it would depend on geometry, geometrical parameters, area, and the distance between the capacitance, the capacitor plate. Okay, multiplied by dV dt, which is how the voltage is changing over time. We did two circuit examples, which were simple. One, we connected the capacitor to a voltage source. The second, I don't remember the order, but we connected the capacitor to a voltage source and a current source. And the part that I was not able to finish last class was this simple circuit tree, where we have a resistor and a capacitor. And as I said, here we're going to look at steady state, but 16b you are going to understand the dynamic behavior of such circuit. Okay. Today we are also going to look at how to come up with equivalence for capacitors and circuits that have capacitors only. And hopefully we'll start capacitive touch, since in the lab the next experiments that you're going to be doing is with capacitive touch. Okay? All right, so let's do this simple circuit tree, and with that we can revise again and how we go about solving the circuits, and catch up or where we stopped. Okay, so the question I have, I give you this circuit, a resistor and a capacitor connected as such, and I ask you, what's U1? How would you solve for that? You say, oh, I know because blah, blah. Or you say, oh, I don't know, but I know the methodology. I will use the methodology. What's the methodology that you learned here? Say, okay, I define a current for each element, which for this one, for the capacitor, I'm going to say IC for current of capacitor. And I define a current for the other element, which is the resistor. I'm going to call RIR. Then you go and say, okay, there will be a voltage across this element. And I'm going to say, okay, so I will use passive sign convention and say there will be a voltage across this element that I'm going to call VC. And I will define a voltage across this other element resistor here that I'm going to call VR. Just for simplicity. Now we solve for U1. We don't know the currents, we don't know the potentials, but we know the value for resistors and we know the value for capacitors because those are defined. Those you pick and you put them there in your circuit. Okay, so we are always looking at steady state in this class. 16A is only steady state. What is steady state? Is we say that the voltage across the capacitor is constant. Okay. So if the voltage across the capacitor is constant, that simplifies our lives a little bit. Why? When we look at such circuit. Because if I write the current elements definition for the capacitor, is going to be capacitance times dV dt, where V here is the voltage across the capacitor, and I'm saying we are analyzing circuits considering steady state. Steady state means the voltage, in this case, voltage is constant. If the voltage is constant, that means that this term here goes to 0. Yes? That means the current in the capacitor is 0. We actually saw that this, the change in current in the capacitor is really, really fast, right? Capacitor charges really, really fast. In the demos that we had here, we always told you, oh, try to watch the current, but, you know, it was hard to watch the current. Because when it gets to steady state, current, no current. Okay, so that means IC, in this case, is 0. If we go to apply KCL, because I define two currents, and I'm going to use KCL to U1 because I want to solve for my unknowns, which are U1, IR, and IC. What would KCL say for U1? Current coming into the node is equal to the current going out of the node. So we write, thank you. It was a whisper, but I heard it. It was IC plus IR equals 0. I think it was actually IR plus IC equals 0. Yeah? I know. I could hear. Okay. Oh, but we already found by elements definition for the capacitor that IC equals 0. IC equals 0. So if IC equals 0, it means that the current going through the resistor is 0 in steady state. All right. I still wanted to define U1. I'll give you the punchline at the end. Okay. How would I define U1? Well, U1 is the potential that is across here. It can be written as the voltage across these two elements. So I'm going to apply Ohm's law. And Ohm's law would give me that VR, voltage across the resistor, is equal IR times R. But VR can also be written as U1 minus 0, which is going to be equal to 0, because the current is 0. Okay, so I know that U1 equals 0. Wait a minute, I could have known that from the beginning because there's no voltage source. I told you it was steady state, there's no current. Okay, but it's nice to see that the laws still apply. But in our designs, what does it mean? If you see such a block by itself, and you know that the current is equal 0, if the current is equal 0, how can you model this circuit? In the most simplified way, what's the equivalent element for this circuit? Open circuit. Oh, are we going to use this? Yeah, put it in your pocket, okay? So something that might start the class for you as, oh, we never did this. What? Resistor, capacitor. We defined a few boundary conditions and arrived to the point where you can use that as an open circuit. Okay, so with those three simple circuits that I gave you, using capacitors, you can do a lot of combinations together with what I'm about to talk about, which is equivalence. So let's say, what's equivalence? We use equivalence when we have a complicated circuit that we want to simplify and find current and voltage, or when we have something that is unknown, a box, an electronic device that we don't know how it has been made. Then we go and we measure that device either by applying a voltage or applying a current, which we called, in the case of resistors, we called I-test and V-test, right? We measure the IV curve, and then we know how that box is behaving, which means that we can then model it using the Thevenin equivalent circuit or the Norton equivalent. Very good. And we had this whole methodology where we are going to apply to capacitors too. So if I have a box where it's full of capacitor circuits, only capacitors, doesn't matter how they're connected. That's why I didn't connect them. I just put like a mixed bag of capacitors that form that circuit. We always have two nodes or two leads that you can take where you can apply our I-test, V-test. In this case, when we apply our I-test, V-test, we define that in this box that we can look at as an element, there will be an I element, there will be a voltage across here that we have been calling V element, and we can use all the methodology that we learned so far to solve that in a way that we would come up with an answer that would say, okay, the equivalent capacitor for that box is CX, we will find that, and the equivalent circuit for this would be a capacitor equivalent that will have an I element and a voltage V element across it. So this is where we want to arrive, right? We want to arrive there, where we have an unknown, complicated, or not necessarily complicated, get to a circuit that we can model the behavior as one capacitor, the equivalent capacitor. So far, so good. Just refreshing what we have done for resistors. Okay? Oh, and then our steps for the resistors were, we had first step, find V Thevenin or R Norton. And then the second step was to find the resistor equivalent, in the case of resistor, where we had Ohm's law, or we had the relationship, the IV relationship to find. In the case of capacitor, because the current of the capacitor is given by capacitance times dV dt, our equivalent capacitor, this, is going to be I current of capacitor, the element capacitor, divided by the gradient of the voltage, or the change of voltage with time, dV dt. Okay? So when we do our I test, V test, this is what we are going to be looking for. What is C equivalent? So we have two methods, as I said. Our methods was, depending on the circuit that we had to analyze, we chose sometimes that we would apply V-test because it would make our equations easier when we knew that voltage across the elements would be the same. In case of other circuits, depending on how the elements were connected, we would choose to do I-test because we knew that the current going through the elements would be the same and would make our equations simpler. We also had some conversations about, oh, does it matter if I apply I-test, V-test? And the answer was, it doesn't matter, but depending on how you choose, you might end up having to deal with more equations than others. So in most cases, we try to simplify. Okay, so method one, what was it? We have done this for resistors. We apply I-test, and then we measure V-test. Here, we are going to measure V-test, dV-test dt, because we know that that's going to change with time. And we are going to look at the steady state. Or you apply V-test, which is, in this case, is going to be dV dt, and then you measure I-test. So just so you have in your notes, what would we do? If we wanted method A, where you apply I-test, I would come to this unknown box, and then I connect a current source here. Let me make the current source, it's a bit small. I connect the current source here, and I call that I-test. And I would measure the voltage across here, which would be, or the voltage change, which would be V-test dt. Okay? Very similar, but different because the IV characteristics for the capacitor is different. And we saw that, right? We saw that with time, the voltage across the capacitor as we were charging was changing up to the point where it equalized the external voltage source that was doing the charge. All right, now the second test, or the second method, is to apply voltage. Well, but it's a voltage that is going to vary over time. So from now on, when I want, let me make this bigger. When I want to put this dV dt, we are going to put squiggly signal like this. What does it mean? It's changing over time. And actually, a lot of the signals from sensors are not constant, right? So they are actually varying signals. You're going to play with that way more in 16B. Okay, so I am applying dV test dt, and because now I'm giving power to the circuit, there will be a current. Let me make in a different color here. I-test. Okay? And then we form IV curves, and with our IV curves, we can write that the capacitance equivalence for that would be I-test over dV test over dt. Okay? Questions so far? I'm going to do examples next, but this was just a refresher of the methodology, the equivalents, the Thevenin and the Norton equivalent applied to capacitors. No questions. It's either very clear or very confusing. Oh, okay.
Do you want to ask a question? Oh, hold on.
How do you apply a DV test over TT? Like
How do we apply? Externally, right? You come there. Remember, Mickey brought his voltage supply. You apply and you go and change, right?
Oh, okay.
Yeah, it's a real thing. It's a power source. And then you measure current, or you go apply current, measure voltage. Excellent question. I'm waiting.
So when you apply DV test over DT, how do you know I test isn't also changing?
I couldn't hear you, sorry.
When you apply DV test over DT, how do you know I test isn't also changing?
I test is also changing. I test will be changing, right? Up to which point? Up to the points that you charge your capacitors.
And then it becomes zero.
Yes.
So when you calculate C equivalent as I test over DV test by DT, I test is changing, right? So how?
I test changes very quickly. We are going to do examples, okay? I test changes very quickly when you are charging. But then, since we look at steady state, we know that voltage will be zero. But let's do an example. Okay, here, example 1. I have two capacitors. I connected the capacitors as such. Then I ask you, now we are going to do the opposite, right? Now I give you the circuit and I tell you, give me a model or find the equivalence. Find the equivalence capacitor here. What is, how could you simplify this circuit to a point where it was only one capacitor and you could write the IV curve for one capacitor? So, two methods. Apply I test or DV test DT. Which one would you apply in this configuration? DV test. DV test, yeah? Everyone agrees, DV test? Great. Why?
Since the capacitors are connected in parallel, the voltage across both of them will be the same.
That's
so
right,
it's easier
because
to
we
control.
learned that if we apply DV test in this case, we know that the voltage drop in this element is going to be the same as the voltage drop in the other element. We learned that from our resistors. Yes, thank you. So I'm going to add here my DV test squiggly, which is DV test DT. Because of this external component that I'm bringing here to close this circuit, I'm going to label everything else in red. I know that this will correspond to I test, a current that is now introduced in the circuit. Next, we should label our nodes. So I have a node down here, which is the node that I'm going to pick to be 0, reference node. Then how many more nodes do we have? We have the top node, which I'm going to call U1. Very good. Then I can define that there will be a current here that is a IC2 for capacitor 2, and there will be a voltage drop VC2. Do the same thing for capacitor 1, IC1, voltage drop VC1. We labeled everything. Now we can apply our methods to look at this. Okay. First thing we know is that, well, let's do first elements definition. Let's do elements definition for each one of the capacitors. Okay. Pick capacitor 1. For capacitor 1, how would I write IC1? Definition, element definition. IC1 equals?
I see one too.
You see one too?
Yeah.
I see one. Okay, IC1 equals C1 dVC1 dt. Thank you. Okay. IC2 C2 dVC2. Very good. What do we want to solve for? Potentials and currents. We have current, we have to write these voltages as potentials. So I would say for IC1, current 1, it will be C1, capacitance 1, D1, oh, okay. What's VC1? VC1 is the voltage across here. And this element is between 0 and U1. So the voltage across that element is U1 minus 0, which we can write as U1. So I will write, instead of dVC1, I will write du1 dt. Why did I do that? Because by voltage definition, I can write that VC1 is equal U1 minus 0. What about VC2? What about? Well, VC2, we decided to do a V-test because we said, oh, the potential will be the same. And look here at the diagram. Capacitor 2 is between nodes 0 and U1. So by voltage definition, VC2 is equal U1 minus 0. That means that I can write here this capacitor, the current for capacitor 2 as equal to C2 times du2 dt. Just substituting. Oh, du1, sorry. There is no u2. Sometimes. Okay. Okay. Makes sense? All right. Now we have current represented in terms of constant and our unknown, which is potential 1. Let me fix this. du1 dt. We can apply KCL. Let's apply KCL. If we apply KCL to node 1, what do we get? Oh, wait. Think. KCL for node U1. Oh, current coming in equals to current coming out. What's the current coming in? I test. What's the current coming out?
IC1 and IC2.
Oh, yes. IC1 plus IC2. Nice. Nice. Very good. That means that now we can say, because all we want was to find the relationship between I test and dV test dt, so that we have the capacitance equivalent, right? So let's write now I test equals IC1. IC1 is C1 du1 dt plus I2. I2 is C2 du1 dt. Okay.
No.
Yes.
No.
Uh-huh.
You see what's happening?
You see what's happening?
No.
U1. How does U1 relate to V test? They are the same. Very good. So now let's write again to make it even more clear what's happening. I test is going to be C1 times dV test dt plus C2 dV test dt. If you isolate dVd test and I test, what do you get? You get I test equals C1 plus C2 times dV test
No.
dt. Okay. What was the definition for our capacitance equivalent? Well, the equivalent capacitor would be given by I test over dV test dt, which we have right here in front of us. So in that circuit, what's the equivalent capacitor? Yes. C equivalent will be equal to C1 plus C2.
C1 plus C2.
Thank you. Cool? Wait a minute. We started off by saying, oh, they were connected in parallel, but now we are saying that the equivalent capacitance is the sum of the two, which is exactly the opposite from the resistor case, right? So that's why it's not good to just memorize things. It's good to see where they came from, because it makes sense why. It's not magic. It's because how the elements behave. Are we good? Yes. Oh, I sensed confidence. Next. Okay. Example 2 might not be surprising. Now I give you capacitors connected in series. Okay, how would we do this? Oh, you might know the formula by heart, but let's use our methodology to get to the formula. What are the options we have? The options are, I want to simplify, I want an equivalent circuit, therefore I have two choices, apply dV test dt or I test. What would you apply in this case? I test, because when elements are connected that way in series, the current will be the same. Very good. So let's do it. Yeah? Okay. You can go ahead. While I write, you can write too. So let me do it in red, just because it's our I test. We are going to come here, connect some other element where we are going to apply a test current, I test. And we know that in that test current, there will be
I thought you were giving them time.
a
Sorry.
V test. Were you ready to party, Mickey? Oh, they could chat.
No, I
they
thought
could
you were giving them
dance.
some time. And so I thought it was like, oh,
but there are capacitors there we have
let's
to deal
play
with.
some music.
Okay, I'll give you
working
some
on it.
time for music next, okay?
Thanks.
Okay. All right. Let's label everything, everybody. Okay, I'm going to make this lower node here 0. And the top node U1. Are those all the nodes we have? No, there is another node. A node between the two capacitors, which I just erased here. Okay, U1. Why does the eraser do this? Okay, U1, and then we have another node here, which I'm going to name U2. Remember how I used to get mad at you in the first semester we taught together?
No, you weren't mad. You were just
I
looking.
was just like
No.
disturbed.
You're looking at me. It's
I
like,
was like, stop interrupting. Now I even dance to our interruptions. Oh, we evolved.
it was an interruption.
Yeah, good partnership. Look, I can even interrupt myself now and be good with it. I
Wow,
feel like I evolved.
You've grown so much.
You
grown so
changed me, Mickey. You changed me. Thank you.
Aw.
Okay, back to class. Okay, so I labeled our test in red. I'm going to label all the other elements now. Since we have capacitor 1 and 2, I'm going to call the currents IC1, and then the other current will be IC2, and voltage across VC2, VC1, because we made decisions based on the knowledge we have. We did say from the beginning that I test was going to be equal to IC1, which is equal to IC2. Yes? Are we good there? That's a good point to start, right? Because we made our decision of connecting a current source based on that, because we said, okay, that's going to be much easier. So this would be if we apply KCL. We find this. All right. Now let's do elements definition again. Elements definition for our capacitors. Elements definition is exactly the same as we did before. So I will say IC1 is going to be equal C1 times dV C1 over dt. And IC2, what is IC2? C2 times dV C2 over dt. But now we have to be a little bit more careful about our voltage definitions. I'm going to make here in the corner voltage definitions. Because now we have one more node, right? Okay. You tell me, what is VC2? The voltage across capacitor 2. You come here, take a good look at capacitor 2. Capacitor 2 is between nodes 0 and U2. So what's VC2? Thank you, U2 minus 0. Very good. What's VC1? You come here, you take a good look at capacitor 1. Capacitor 1 is in between U2 and U1. So voltage in capacitor 1 is U1 minus U2. Thank you. And finally, we cannot ignore our V-test, because that's what we are after. We are after the relationship between V-test and I-test. V-test is, you go there, you look here, V-test is between 0 and U1, so V-test is equal U1 minus 0, which is equal U1. Very good. Now we start substituting for our capacitors, because what we are looking for is a relationship dV test dt and I test. So we have to write everything to get there. Shall we?
Yeah.
Okay. Let's do first for capacitor 2. Orders here. I'm going to write in green for C2. So you understand what I did later. We do have a current relationship for C2, which gives us IC2 equals C2, a constant, dV C2 dt. Okay. That means that we can substitute VC2 in here, which will be U2 dt. Wait, what did you do? Okay, I took VC2 here, which we found it was equal U2, and I put here instead of V, okay? All good? That sounds simple because from here, since I know that IC2 is ITest, I can write next that I have ITest is equal C2 du2 dt. Okay, now I have one equation that relates ITest to potential. Next, let's do the same analysis for C1. Let me put C1 here underneath the diagram for C1. For C1, we know that the current is IC1 equals C1 times dVC1 dt. But wait, because we know what's the relationship between V1 and potentials. So right here, we have that dVC1 is U1 minus U2. So instead of writing dVC1 in the current equation, we can write d U1 minus U2 dt. All good? Following? Happy? Yeah? Okay, now it's algebra. Let's do it. Do you want to do music now? No, I'll do it with them and then. Yeah? Okay. Not too loud because I'll be talking. Okay, we also know that IC1 is equal ITest. Oh, how do we know? Because it was the beginning of our assumption here, that ITest would be IC1. Okay, so I'll keep rewriting things here, and I will write the following.
Snake jazz.
Okay. Okay, you can stop now. We go back to that. So we're going to write the following. ITest over C1 equals du1 dt minus du2 dt. Good? Followed what I did? I just took my C1 from this side of the equation, put it dividing there, and just to rearrange things. What can we substitute here in our equations? Since I know, okay, I will go one way, you can go different ways. I will write this next in the following. I know I'm going to write du1 dt equal du2 dt plus ITest C1. What did I do? I just rearrange. Signs changed. There's no minus anymore. Okay. Next I can write this as equal ITest over, hold on, I'm going to do one step before. Okay, we know what, before you get confused, you know what du dt is, right? Because we got it there from the top. So we had here du dt that we found from substitutions. So I am going to write now this equation as this is equal I test over C2 plus I test over C1, which came from the other equation when we were looking only at capacitor 2. Oh, now that we know that U1 is equal V test, we can write this first term here that I put separately for a reason, because I wanted to find V test. We can write this as d V test dt. That is going to be equal I test yes, plus 1 over capacitor 2 plus 1 over capacitor 1. Wow, what is this operator? Parallel operator. So when we do our I test, okay, let's do it. What is our capacitor equivalent? Capacitor equivalent for our methodology here is I test over dV test dt, which if you rewrite is going to be equal 1 over 1 over C1 plus 1 over C2, which gives us a parallel operator C1 C2 over C1 plus C2, which is C1 parallel C2 for short. Wow. I hope some of you were once upon a time confused about the rules for resistor, the rules for capacitors, and now there is a reason, okay? So when you connect capacitors in series, then the parallel operator is the result for the equivalence. Go ahead.
Why did we assume that I test is equal to I1?
Because we have two components here that are connected in series, right?
Okay, that makes sense to me.
Yeah.
I'm seeing that now.
And that's why we chose to apply I test, not V test in the first place. Because simplifies things, right? Yeah. Thanks for asking. Okay, now, Miki, was the moment that I wanted you to put music and let them work. I'll give you 2 minutes to tell me what's the equivalent capacitor in this circuit. Actually, 1 minute. You guys are very smart. That's jazz?
Snake jazz.
Snake jazz. I should give you some of Mia's recording. She's doing so amazing. Yeah? Oh, the jazz snake is 1 minute? Okay. I was going to go for it. Half an hour left. Great. Okay, do we have an answer? Who wants to say the answer, how you solved? Put your hand really high up so Mickey can see you and run to you. He's, yeah.
C1 times C2 plus C1 plus C3 all over C1 plus C2 plus C3.
Okay, okay. Did everybody get the same answer? What would you do? Okay. What you're looking for is something that looks like this, where you have only one capacitor, where this capacitor is your equivalent capacitor that is sitting between nodes A and B, right? So what do? First, you can find what is the equivalent capacitor between C2 and C3, right? Is that what you did? So I'm going to color this box, and we are going to find what's the equivalent capacitance for that box, and what is that? And I'm going to call this C equivalent 1, box 1. What would that be? C2 plus C3. Very good. Then you make a different circuit that looks like you have C1, and then you have C equivalent 1, which is C2 plus C3. And then what's the equivalent capacitor between these two nodes, A and B? Now it's the two capacitors in series, so you can say C equivalent, now final, is equal C1 parallel operator, C equivalent 1. Yeah? Sounds good? Great. Move on. Now you have all the, okay, here's just slide concluding, where you have all your formulas that you were made to memorize before. Okay, capacitive touch. Now you have all the tools that you need to understand capacitive touch. We like capacitive touch because it makes our lives much easier, right? We use capacitive touch every day. Phones and iPads and computers and so on. How does it work? How is it fabricated? In capacitive touch, you have capacitors. These capacitors are formed, some things, materials that are deposited during the fabrication, where you would have one lower plate here that is represented in this side view, which is a metal. Then, so you deposit the metal, you go there and then you pattern the metal, where you make very fine structures that will give you very high resolution. So lots of fine structures in that metal. It's not a blanket metal, it's patterned, so it's very fine lines. Okay. Then you go and you deposit a material that is a dielectric. So let me color our dielectric here, pink. So you deposit a material on top of those metal lines, and you know that this material is an insulator, does not conduct current in that direction, right? It isolates the conductor that was patterned on the bottom, you deposit on top. You're making a sandwich, a stack. Okay. Then you go and you deposit a different metal. So let me call this is dielectric. And you deposit a different metal, which you would again deposit in many, in a patterned way. So you would have another pixel here, another pixel, and so on. And so this would be a metal. A metal. And then you deposit another layer on top, which is the layer that you interact with. Another dielectric. Let me use a different color to represent the other dielectric, green, which will be here. Okay, what's the dielectric that you interact with? What do you touch when you use capacitive touch? Glass, exactly, glass. Chances are this is built, starting from glass, deposit metal grid, deposit another dielectric, deposit other metal grid, flip it, connect with the rest of the electronics, and you're interacting here, okay? This is how capacitive touch screens are made in a simplified way. If you had to look at the top view, you will have, so I'm looking here at the top red metal that we deposited here to form more pixels. So you would have that metal going in one direction, the lower metal going the other direction, such that they cross. And where they cross, you have this structure here, right here, where they cross, okay? So here's looking from the top, as we typically look at the screen. And the side view is if you cut that part and you looked from the side, how it looks like, the cross section. Okay, so that seems pretty simple. If you have two metals and the dielectric in the middle, what's that element? It's a capacitor, right? So that means you can store charge in that element because you have metal separated with a dielectric. So you have a capacitor. In your notes and here, that's represented as C naught. What does it mean? C0, C naught is the capacitance that is there because the manufacturer chose carefully the dielectric that they wanted to use between those two metals, such that it would give the best resolution, the best performance as you touch. Quick answer. Okay, for us, we are learning this. We are going to look at this as if I have two nodes here. One that is named E1. I'm going to change the name in the next slide, but for now, we can keep what's in your note. And then we have another node, E2, and in the middle, formed by these materials, we have C naught, the initial capacitance that you have, okay? And then if we were to look at the full screen, what you would have would be, okay, let me use the same colors that you have. You would have a bunch of, I'll try to draw straight, a bunch of lines going this way, but much finer and much closer together than what I'm drawing here. And then we would have our first dielectric, C naught, this way. Everything okay? Okay. The dielectric that has some sort of dielectric constant over there. Then we would deposit the second metal, which is represented in red here, right? And on top of everything, we have our green that is covering everything, like this. So it's isolated. We never touch metal in a capacitive touch, right? Makes sense? Where are our C naughts? Our C naughts are in all the places where the two metals intersect. But as I said, it's very small features close together, really close together, so it gives you really, really good resolution. Clear? Okay, you got it. I'll just complete here. I made too many capacitors. Oh, there was a defect on the fabrication. Those didn't touch. Okay. Yes?
So with the capacitive touch, then it's still like a grid system, right? Where like each, like when we touch a point, we're like separating.
Yes, still as a grid system.
Can you repeat the question?
Oh, the question was, so capacitive touch is still a grid system where you touch, then you're separate. We're going to go a little bit deeper in the capacitor, you see. Because obviously, I mentioned many times, we can actually discuss now, I mentioned many times that these are very fine, very close together. So when we touch, do we touch only one pixel? No, right? We touch several. Yeah. Okay. Clear so far? Okay. What is C naught? If I ask you, what is C naught? Can you tell me? Yes. What is C naught? Okay. The answer is yes, I can tell you what C naught is. It's going to depend on the permittivity of the material. Whatever material we chose, if I chose a polymer, which I always choose because I work on polymer electronics, I know that the permittivity is low, so I know how to calculate my C naught. If you, in your devices, you probably have much better dielectric. So he said C naught is going to depend on the permittivity of the material. And what else C naught will depend on? The geometry, the area. What's the area? The area is given by the area of how much overlap there is here, right? These little dots that I drew here representing the area. And it will depend also on the distance between the two metal plates. The distance is given by the thickness of the layer that you deposited. Remember, we had a discussion about capacitance. You can change the capacitance, make the capacitance larger by making the thickness of your film smaller. Have to be careful so that there are no defects in your fabrication, but that's the general notion here. Good? Clear? Okay, but this is what's happening with a capacitive touch screen if we're not touching it. Now, touching the capacitive touch screen is part of its operation. So we have to consider what happens to this capacitive touch screen when we introduce our touch there and how it would look like. So let me color my capacitors the same way that I did before. I had the green and the pink. So the green here is representing the glass, just so you don't think it's air or nothing. And then we have the manufacturer's choice for capacitor here to form C naught, right? And of course, this is a very nice form interface. It's not wiggly like that. Okay. So what happens when you touch? What changes? Anybody wants to try? There will be a capacitance. A new capacitance will be introduced. Where is that capacitance coming from? Plus distance? Less distance? Oh, do you deform the glass when you touch? No, right? The glass is solid. You're not deforming it.
I was gonna say that your fingers capacitance permittivity.
The finger adds to the capacitance. How? What's the finger operates as, or what's the function there?
Touch.
Yeah, go ahead.
Surface here. Does it change the surface area?
Does it change the surface area? Keep trying. What is your finger working as?
Your finger is a plate. It's conductive.
Your finger is conductive? Is our finger conductive? Is our body conductive? No? Can we just put our fingers in the power outlet there?
Let's see.
Let's see. You go, Mickey. No, I like you. You're my good friend. Don't do that.
Oh, just put in one. I just put one.
I'll
put in the neutral.
Our finger is conductive. That's right. Our finger is conductive. So essentially, when we touch this touch screen, we are, in practice, introducing a new conductor. So our finger here in the area that we touch with the finger represents another conductor. Now, if I have another conductor, which is my finger, touching a stack of electronic materials where I have dielectric and metal, then I introduce a new capacitance. Yes. And where is that capacitance represented? Well, okay, now I'll ask you again. How many capacitors then the touch, as I showed there, could be introducing? Think. You have your finger as your top metal plate now, your top conductor. You have C naught. Do you agree? Anybody has an answer? Go ahead. You should, he sees 2 extra capacitors. 1, yeah, 2 was the answer that I was looking for. There will be many, actually, many, but there will be 1 capacitor that can be represented right here between the metal plates that we had there, the red metal plate, and then the top metal plates that we have. I'll call that C1, okay? And then, because our finger is much bigger than the structures that we have, there will be also capacitor formed between the finger and the bottom metal plate, which I'll call C2. And that's when I told you that I was going to change the name here. I'm going to call this G, just because it's easier to draw. Yes?
So the red metal is not a full sheet. It's just like columns
patterned
of metal that are scattered throughout the whole screen.
Yeah, it's like this.
Okay. So there'll be gaps where those other.
There will be gaps
are
that isolates those capacitors from each other. Yeah.
Okay.
Yeah. But reality is we are going to touch many of those capacitors, right? Okay, because the finger is on a different scale here. All right. So now let's come up with a model. Do you have a quick question? Okay, ask. Uh-huh. Okay, the question is, let's see if I understand. I drew lots of lines like this, and your question is, how come there is no capacitor formed here? That's a very good question. Actually, it's a lateral capacitor. Typically, the capacitance will be much lower than the other one that's formed vertically because of the distance. Excellent observation. Okay, continuing. We are going to ignore those, okay? We're going to ignore those capacitors. We are looking in the vertical. All right, so let's come up with a model for our capacitive touch when we consider touch. So in this model, we would have a capacitor that is formed by a plate represented by our finger here when there is touch. This is the conductor. And then we would have a dielectric, which is the top dielectric that we interact with in between. And then we have a second metal plate, which is what the manufacturers choose to form those capacitors that come as C naught, right? So this is how our capacitors look like. And we have here, we can access both plates. So here, this is the finger. Here is a dielectric material, glass. And here is a conductor, a conductive plate. Conductor. Okay. Now the problem, right? With every design, every model that we have, we come up with a problem. I ask you, how can we measure voltage or current when a very important electrode or conductor in our system is the finger. How do we do that? Oh, we call finger the ground, but is it a consistent ground? Is it a consistent reference? No, because it's like touch, no touch. So, oh, ground, no ground, right? It's a problem. It's a big problem. How do we solve this problem? That's where you have to take the EECS classes so that you know how to come up with good models, and you can also come up with a good architecture. Architecture. Right? You have to think about the system now, because you have something in your system now that's completely unreliable, completely unpredictable, which is the touch, the finger, your electrode. Okay? So let's see if we can come up with a model. First, let's look at the equivalent circuit. Well, how does the circuit look like? So as I said, we have two capacitors here that are formed only when there is touch, which is C1 and C2. C0 is always there. This comes from the manufacturers. Okay? So when there is no touch, I'll say when no touch, the circuits that we have, and remember I named this G. The circuit that we have is a capacitor C0 that is sitting between the two leads that we have that came from the manufacturer that are E and G. Right? Can you see that? Just what came from the manufacturer, you can go there and probe that capacitor externally between those two nodes. Okay, now with touch, we have something that is slightly different, because we will have our capacitor 1 that is formed right on top of C0, this one, capacitor 1, that is right, that is right on top of C0, right? What are the nodes that are between them? Between C1 and C0, which nodes do I have? E, right? Okay. Then continue drawing our circuit here, our equivalent circuit for this model, and then we have the other capacitor that is formed between the two dielectrics there and the finger that we are calling C2. Now let's label the nodes. Which node is this one, the bottom node here, from your diagram? G. I labeled G because we can make it ground right later. 0. G. That's node G. And the top node, what are we going to call it? F for finger. Very good. And let me color here green so we know what we are talking about. This is the node that is formed because of our finger touch. Do we know how to solve this?
Yep.
Yeah, we just learned. It's fresh in our memory. Yeah? So let's redraw this to focus on how we can, the terminals that we have access to, which is E and G, and find an equivalent capacitor. So try to find the equivalent capacitor. What I'm going to draw differently is just, I'm going to put node E here. Because I have access to node E, I'm going to say, okay, node E is going to be one of my probes. Okay, so if I start with node E, I know that node E is connected to C0. It's connected to C1 and C2, right? So I'm going to first draw the connection of node E to C naught. And then the connection of node E to C1 and C2. Okay, and then C2 wraps around. This eraser today really wants to erase everything. C2 wraps around, and then we have here access to node G. Yeah, just redrew the circuit. Okay, where are our other nodes? We have node F. Where is node F? Where is node F? Between C1 and C2. Between C1 and C2. This is node F. Okay? Now that you have this, you can come up with what was the equivalent circuit. So, oh, sorry. I could further then, using equivalence that we just learned, I could further write this as node E connected to C naught. I know that C naught is always there. And then the capacitor equivalent to C1 connected in series to C2 is E and G. I'm just waiting here. That's parallel, right? The parallel operator, which will be given by C1, C2 over C1 plus C2. So if we had to come up with an equivalent circuit for when there is touch, I will take questions. I see many questions. I just want to finish so I can take all questions. Okay, so when there is touch, our equivalent circuit here, as if there was only one capacitor between nodes E and G, C equivalent, would be equal to C naught, because it's C naught connected in parallel with that other equivalent circuit. So it would be C naught plus C1, C2 over C1 plus C2. Now, the cool part here is that this term here, which is the capacitor equivalent represented here, which is C1 and C2, only appear in our model when there is touch, right? So if there is no touch, you have the capacitance that comes from the manufacturer. When there is touch, you have extra capacitors, which we called C1 and C2 here, which were connected in series, and they are adding here, because they are parallel to the C naught that was there, that are adding. So it's a separate term. And this one, in our model, we are going to call C delta. What does it mean, C delta? Delta represents change. So it's the capacity change that happens when there is touch. Okay? So when I asked you what happened when you touch, the answer was there will be an additional capacitor. What is this capacitor? We came up with a model that forms two capacitors that are connected in series with C naught and in parallel with the equivalent, and then we know what is the change in relation to that capacitor. We have time for a couple of questions. There was a question here. Your finger likes a conductor, yeah. It's a conductor, it's not a perfect conductor, but it's enough to form a capacitor. Yes, go ahead. Your finger doesn't get charged? Oh, okay, it's the resistance. Okay, I will see you on Thursday where we are going to measure this. Very good.